I'm Paddy Neumann, and I'm a rocket scientist. I'll also come out of the academy, so I'll be standing here behind the lectern and pointing at things. Please take notes, there'll be a quiz at the end of the period. So, Space Missions 101. I'd like to answer the last part of the intro first, why we do it at all. Space is cool. You can see rocket launches, you can see, I'll play with that a bit, there we go, no worries, better calibration. Rocket launches, you can see ground stations, you can see the data that comes back. That picture at the, at top right, that's the south pole of Jupiter from the Juno spacecraft. No one had seen that before about a year ago. And you can get very high resolution images that look like a surrealist, impressionist painting. You can go down to Officeworks and get it blown up onto a massive canvas and put it up on your wall, and it looks fantastic. And of course, all the data's got to come back through somewhere, and there's one of the ground stations that ESA uses. That's actually their Mission Operations Center, where they have some of the work of communicating to the space station, as well as a bunch of the European Space Agency probes around the solar system. So that's one reason of doing space. Additionally, space is inspirational. Space affects us all. Space, because it is cool, makes people want to do it and affects society to help encourage us to keep doing this. So you can see there's a stamp from the Soviet Union to commemorate Sputnik. People were sufficiently proud of launching stuff into space, they put it on the stamp. That's the 30 kopeck, 30-cent stamp. You'd put it all over the place. It was great. You also have deep and abiding cultural institutions such as the Parkes radio telescope being used for deep space tracking, and interesting cultural fusion activities happening in the dish during downtime. This is still happening today with smaller nations, newer nations, emerging nations getting into space as well. There you see people from a university in Ghana with GhanaSat-1. Ghana now has a space program. They've put material in space. Tiny Ghana, recently decolonialized Ghana, has a space program the equivalent of the Soviet Union in 1957. It's incredible when you think about it like that. Space is also big business. One of the reasons people do space is that you can use it to turn a dollar. You can use it for satellite communications. In fact, this is the dominant monetary stream. If you have a look at the breakdown of commercial spaceflight and commercial space industries, you can download this from the US Department of Commerce's annual commercial spaceflight compendium. About 97.5 billion US is just satellite TV. Just satellite TV. Phone and internet come in at about 30 billion a pop. So people really like watching their football, and it doesn't matter what particular sport you happen to call football. There's also position, navigation, and timing. GPS is being used everywhere around the world, and the chipsets to handle those GPS calculations, they're not the simplest things in the world to make or build, and someone's got to make and sell them, so people do. They also get used for timestamps, those GPS signals. GPS works by telling you when a signal was transmitted from an orbiting satellite. You collect enough of those timestamps, you can figure out how long it took each of those signals to get to your phone, and with a bit of maths you can figure out basically where you are. It's kind of like triangulation. But you can also use those signals to figure out when you are, to time things like financial transfers from not just stock markets but also ATMs. You can do it for Earth observation. People have used this for decades for satellite reconnaissance, for various shadowy objectives of the military. But you can also use it for weather. You can also use it for mapping. You can use it for agricultural sensing to determine how much moisture you have in your paddocks. In fact, some of them are sufficiently high resolution, you can figure out what part of your wheat field needs more water, or with a different sensor, needs more nitrogen or phosphorus, so you can better target your agricultural inputs. You can also use various space things for space-enabled services, such as augmented reality, precision agriculture, autonomous vehicles, autonomous navigation, all these things that are enabled by space assets. And you can do this in such a way that you can use it to turn a buck. But space is also hard. You can see some examples of when things go wrong. At left, there's a monument that has since been vandalized, commemorating 3 cosmonauts who fell to their deaths in Kazakhstan. In the middle is a piece of card left at the Apollo 11 site. Sorry, no, that's the Apollo 15 site, together with a small sculpture to commemorate all the ones that were lost. At the time of that printing, the Soviets hadn't told everyone of all of their fatalities to date, and at the end is Challenger. So, in order to make it less hard, in order to make it more dependable, we standardize and systematize. And these standards and procedures exist for a reason. That image shows you one reason why. Everyone does this. NASA, the Europeans, the Russians. And one of the standards breaks the mission segments down into 4 segments. And I'm going to talk about those segments as my Space Missions 101. They have a launch segment, a space segment, a ground segment, and a support segment. And they're all pretty self-explanatory, but because I come out of the academy, I'm going to explain them all. Fantastic. So launch segment is what it says on the tin, because if you wanted to have a space mission, you've got to put something into space, right? And whatever does this is part of the launch segment. There you can see one of the wonderful, exciting launch vehicles going up. I believe that's Titan II from memory. Primarily the rocket and all of its supporting infrastructure is the launch segment. Their infrastructure includes the launch site, though some people will also fold launch site into ground segment because it stays on the ground. The factors to consider with your launch segment are cost. How much does it cost to have your rocket? How much will it cost to operate your rocket, to fuel your rocket? How much payload can you have? What orbits are possible with that launch vehicle from that launch site? What happens when it goes wrong? And this is space. Things go wrong all the time. Try and make your failure modes non-catastrophic. And as part of each of these segments, I'm going to talk about what people are doing here in Australia. Quite a few of this will be here in Adelaide, but Gilmore Space is not. Gilmore Space are a Queensland-based rocket company. They also have an office in Singapore, but they do a lot of their work near the Gold Coast. And they're looking at launch for small satellites under about 400 kilograms. In 2016, they had a lot of success. They were the first launch of a 3D printed hybrid rocket. A little bit of background, when you're talking about chemical rockets, and chemical fuels are used a lot for launch, you've got a couple of main types. You've got liquid fuels, where you mix 2 liquids and they burn, or maybe one liquid that explosively decomposes and you get the exhaust coming out the back end. Or you get a solid rocket, which looks like a tube full of high explosives, and you light one end of it and you hope for the best. What Gilmore Space is doing is something a little bit different. They have a solid fuel, which is a waxy, paraffin-like material, and they've got a liquid oxidizer. In their case, it's high-purity hydrogen peroxide. And when they pump the oxidizer through the fuel, it burns and it goes out the back end, and they get thrust. Thing is, hybrids have a lot of potential benefits, but actually making them work is really difficult. Rocket science and the mathematics behind it is something we've been doing for centuries. It's the engineering that's the killer. However, in 2016, they were the first mob to launch one dependably. In fact, I think it was their first go, and none of them have blown up since. Recently, they were doing some static fire tests where they put their rocket engine down on a platform, bolt it down, and fire it off. If you look at various mobs around the world, you'll see people tend to fire this downwards into a trench full of water, both to deal with heat and acoustics. NASA's Stennis Space Center in Mississippi actually has a bend of the Mississippi River that they fire their rockets into, because these are the big rockets. These guys are very Australian and fired into the dam at their parents' property. And earlier this year, they had a 70 kilonewton engine test fire. That's 70,000 newtons. That's about the amount of force you need to hover 7 tons, just holding it up. And they're planning on putting a few of these rockets on the back end of a few of these engines on the back end of their rocket to launch stuff into space with. And they're really quite proud of this because it's the highest thrust ever achieved for a hybrid motor. And in comparison, one of the rocket engines on the back end of an Electron rocket from Rocket Lab in New Zealand, a single one of them at sea level will do 18 kilonewtons. Beat that, Kiwis, go on. And they're planning, well, sorry, these flights are a little bit old. They're planning a launch to 50 kilometers altitude later on this year to demonstrate that this thing actually has legs and can go places, with a launch to low Earth orbit in a couple of years' time to send a couple of 100 kilograms of a payload into space. You've got to launch from somewhere, and there's a bunch of places you can launch from. There's a new mob here in Adelaide called Southern Launch, who want to launch small sats into highly inclined orbits. Two main types of orbits. You can either orbit at a fairly low inclination, which means you go around the equator, and that's great if all you want to do is look at stuff pretty close to the equator. But a large part of the world is not pretty close to the equator. So if you want to look at these dependably, you go over the poles in a highly inclined orbit or a specific class of orbit called a sun-synchronous orbit, and you have a large number of small satellites basically making paths looking like you're cutting slices into the skin of an orange. And the best place to launch a satellite into these orbits is somewhere a fair way away from the equator. This is what Rocket Lab in New Zealand is doing out of the Mahia Peninsula, and Southern Launch would like to do this from the south coast of Australia. Because if you're launching southwards from the south coast of Australia, there's a whole lot of ocean that your rocket can fall into if something goes wrong on the way up. If it gets a little bit further, it might ruin a penguin's day, but they don't have any government representation, so the penguins can't complain too much. They reckon there's a huge market, and I tend to agree with them. These are the sorts of satellite orbits and satellite launches that people will be looking for, the very large constellations, thousands of these small satellites for mobs like Facebook and OneWeb and other 3 billion, and it keeps rolling along. They're also in the same orbits that smaller constellations of only a couple of hundred satellites that other people are putting up for Internet of Things connectivity, and I'm sure you'll hear more about that from Flavia. Launch up over the Bight, yeah, no worries. They're planning for a suborbital launch with a commercial sounding rocket later on this year, with big plans for the future. Because after you've launched, something will be in space. So the space segment is, funnily enough, whatever you put up into space, right? Because otherwise it's not a space mission, it's a lovely little hobby you've got there. And it could be probes, satellites, space stations, capsules with people inside, no worries. And this also includes the subsystems of these complex and intricate bits of machinery. Communications, propulsion, cameras, sensors, the command and data handling side of things, attitude control so you can make sure your satellite's pointing in the right direction. All these bits need to work. And the data that is produced by these sensors, that's kind of the goal of the mission, right? It's what you're doing. It's the point of the vast majority of space missions is not to just put something in space. It's to put something in space that'll then do something and then tell you about it. This way you can actually learn stuff. Or, turn $1. Otherwise, we do something else to get it. Drones are pretty cool. High altitude balloons, high altitude unmanned aerial vehicles can do a lot. Some things, however, space is the best way of doing it. And when it comes to the space segment, again, there are Australian mobs doing stuff. There is Innovore Systems. They've got a booth out in the walkway. You can have a look out towards the river while you go out there. They do satellite hardware. They do the design, manufacture, and integration of hardware. You can see some of their kit there. And they've tried to focus on some turnkey solutions for some upcoming missions such as Earth observation and space object detection and tracking so that they can assist with space situational awareness. There's a whole lot of space junk up there. People with operational spacecraft want to know where it is to as high accuracy as possible so they have a better idea of when they have to dodge. Because if your satellite's, a meter in diameter and you know where your satellite is and where a piece of space junk is to within plus or minus 10 meters, there's going to be a whole lot of empty space where you're not exactly sure if it will intersect. But if you can reduce that error bar to by a significant degree, yeah, that'll have value to someone. Yeah, no worries. Then there's my mob. We're doing in-space electric propulsion. Here you can see a pretty picture of our plasma thruster in action, utilizing a piece of steel to make plasma just the same way that a welding arc does, and then use that plasma as the exhaust to make thrust. Our system is more fuel efficient than anything that's currently in use on space. With the right fuel under the right conditions, it's 3 times more fuel efficient than the current record holder in space. It sounds really cool, and it gets even better when you realize that the equations involve being able to take the fuel along for the next step. You need more fuel to take that fuel with you. So it's literally an exponential dependence. More robust fuel, because we can use stuff that's solid and conductive. And that's steel. You don't have to keep steel in a tank. You need to keep liquid fuels and gaseous fuels in a pressure tank, otherwise they'll just boil away. All of a sudden you don't have any fuel anymore. We use simpler electronics. We can operate at lower voltages so that we reduce the risk of arcs and sparks inside your satellite, making sure you have as less a chance as possible of having a bad day in space. You can use this for orbital station keeping your satellite in the correct orbit, or for transferring your satellite from one orbit to your destination orbit. And this will enable lower mission costs so that you can keep your satellites on orbit for longer, amortizing your investment over longer time periods, or having less launch mass because you have more efficient thrusters to keep your satellite on orbit, or a combination of the above. Additionally, we can enable new mission types. We can expand the cone of the possible by using this higher efficiency fuel to enable missions such as space tugs, asteroid sample returns, which is another way of saying asteroid mining prospecting, wink wink. We can also enable asteroid mining by enabling a broader range of elements and minerals to be targets for mining, including carbon. Carbon is solid and conductive. You can use it as fuel, and there's an entire class of asteroid called a carbonaceous chondrite. This work derives from my PhD. Like I said, I come out of the academy, so this is nicely peer-reviewed. If you really do want to read 180 pages of needlessly dry technical prose, you can download my thesis from the University of Sydney website. And we're doing the commercialization work here in Adelaide. Again, space segment, we have Fleet. You'll hear more about Fleet, but here's a teaser trailer. They're working on communication satellites, specifically to enable Internet of Things via satellite. They're using a particular standard and looking at doing next generation communications backbone for Internet of Things connectivity. It's specifically suited for remote connectivity, and they're readying their first constellation as we speak to enable solutions that need data. Building Australian capabilities again here in Adelaide. My company's in Brompton, Fleet's over in Beverley. It's fantastic. Ground segment. Because once you've put your stuff up in space and it's making data and sending it back, you're going to want someone on the ground listening for it, right? And that's where the ground segment comes in. And that's a lovely picture of the Canberra Deep Space Communications Complex down Tidbin Billaway. These ground segments include mission control, tracking, telemetry, launch infrastructure as well. They're a necessary part of the equation because otherwise you don't get no data. And also includes the end users of that data, because someone's going to be wanting to use the data. Otherwise, you've got this hard drive full of ones and zeros, and what are you going to do next? Ground segments companies here in Australia include Sabre. Sabre Astronautics is a Sydney-based company that are focusing on mission support and operations software among some of their other projects. They can do predictive analytics, including live space weather, and are actively involved in a number of collaborations and partnerships around the world, and also around Australia, including Four Pines Brewery, where they help make Vostok space beer, the first beer that has been certified by someone who actually knows what they're talking about for use in space. I'm a very patriotic Australian. Again, ground segments, Myriota, they're another Adelaide company. They're going with low-cost, low-power, direct-to-orbit satellite Internet of Things from really tiny bits of hardware. That's the CEO, Alex Grant, holding one of their transmitters. One of those can talk to one of their little baby satellites. They don't have their own satellites on orbit yet. They've been working with a Canadian mob, Exact Earth, and using their satellites to prove their concept. But they're looking at doing whatever you want to do. Well, you've got a sensor, you need to get data from the ground to some other remote location on the ground. You can try doing it through a mobile phone, you can try doing it through existing communications architecture, but if that's not an option, going through satellite communications is a better plan, but there's nothing really suiting that end of the market there yet, and that's what they want to do. Founded a couple of years ago as a spin-out from the University of South Australia. They did their first deployments last year, primarily in ag tech and asset tracking, as well as utilities and environmental monitoring. And they're going full commercialization this year, doing some really cool work. Support segment. And the support segment's the everything else that ties it all together. Pretty much. If there's all these disparate bits, but they've got to all talk to each other, right? This includes the legal and regulatory structures, because if everyone did what they wanted to do, there would be less than ethical people doing terrible things. Also includes the manufacturing sites, because someone's got to build all this stuff. Test and validation equipment, because once you've built it, you've got to make sure it meets spec. You've got to make sure it'll actually bloody well do the work, do what it says on the tin. Quite a lot of it's intangible. That legal and regulatory structures, all the processes, all the procedures you've got to follow, they're intellectual property. That's kind of hard to put your finger on. Manufacturing equipment, well, you know, the rest of it is groundside. So for support, we now have a space agency. This is lovely, this is great. We're now on an even playing field with other members of the space community, such as Nepal and New Zealand. This agency is active as of the 1st of July. It's currently headed by Dr. Megan Clark as the interim administrator, who is former head of CSIRO and has done a lot of cool things in the past. Its primary remit is to develop Australian capability and to be industry focused. It's never going to be focused on the large government programs because we're just not the size of the European Union or a superpower such as Russia and the US or China. We do, however, have a lot of keen, intelligent, motivated people developing industrial capabilities here in Australia, and a little bit of help never goes astray. It's also there to enable cooperation. One of the things that you've been hearing a lot is the need to go global as soon as you can. If I just tried to sell my thrusters in Australia, no. So I have to sell all the way around the world as soon as I can, because that's where the market is. It's also a fairly small monopsonic market. There's not many buyers out there for my tech, so the better support I can have to get my boot in the door, to make sure people know about the technology, know that it's real, to do verification and assistance and testing. This helps my company do its thing. It helps build Australian domestic capabilities so that we can get more of the global space market back here in Australia for that jobs and growth that I hear so many people talking about. Additionally, to help with this, there is the Advanced Instrumentation Testing Centre, which is out at Mount Stromlo near Canberra. They do ground testing for space systems, and they've got a lot of exquisite hardware to do this. They've got clean rooms to do assembly, they've got anechoic chambers for electromagnetic interference, and they've got a large vacuum chamber they call Wombat XL for thermal vacuum testing. It's huge. It's 4 meters in diameter, 5.5 meters long. You can put a spacecraft in there. It gets pumped down to the pressures you'd expect at about 800 kilometers altitude, and then it goes through all the thermal cycling you'd expect to happen on orbit. They can also do the vibration testing you need to do before you send something up on a rocket, because you don't want it shaking apart. It's part of the Australian National University's School of Astrophysics and Astronomy, and they do excellent work. So, now that we've gone through the segments of a space mission, there's always going to be opportunities, there's always going to be gaps, there's always going to be a hole that someone else can come along and fill. So, growth opportunities. Space is global, so we look at the global sectors. Large sectors are hard to enter. They're already pretty large. It's going to be difficult to enter from Australia because we're not a particularly space-capable nation. Government are always going to want to do government programs to justify taxpayer dollars. The TV segment is huge and pretty well locked down. Ground equipment and GNSS chipsets, GNSS Global Navigation Satellite Systems, that's GPS, European Galileo, GLONASS from the Russians, all the various position navigation and timing systems. That equipment, difficult to manufacture in Australia and do so at a competitive price. It's probably not a good idea to try and do those sides of things. However, some smaller and newer sectors are more open, more ripe for disruption, and if you do it just right, you can disrupt the bigger ones as well. So identify niche capabilities with global opportunities and target some markets, prove the concept, scale to meet market demand, and do what we can do here in Australia. I've talked a bit about it in separate, but to put it back all together, currently there's a bunch of work happening with Defence Science and Technology. They're doing tech demonstration missions such as Biari and Buccaneer, and doing ground station support work, and they're doing excellent work to build Australian capabilities. There's other parts of the Defence White Paper with about 10 billion in total research over the next couple of decades. There's work happening along these lines. The Bureau of Meteorology, CSIRO, and the Australia Telescope National Facility are all doing interesting things to do with satellite communications and ground stations. UNSW has campuses both in Canberra and Sydney working on space missions, on the hardware, on the architectures, on the ground side support, and mission capability proving. The University of Queensland is continuing its excellent world-leading work in hypersonics. The University of South Australia is working on telecommunications, engineering, and all the various aspects of this. There are some other academic projects going around the country as well, some of them fairly small. You might have a couple more people working on propulsion systems, communications, sensors, command and data handling, better software kernels, rad-hardened computer hardware, etc., etc. When you look at the segments, however, we've got people working on launch, we've got people working on the ground segment, we've got people working on the space segment, and the support systems. And various people are working on payloads as well. So you've got Earth observation payloads coming from Fluorosat and Aerospace Systems. You've got space situational awareness coming from HEO, UNSW Canberra, and the Australian Centre for Space Engineering Research at UNSW in Sydney. You've got communications payloads from Fleet, Innovor, Myriota. You've got localization and mapping systems coming out of a couple of academic institutions, ACSER, as I mentioned earlier, and the Australian Centre for Field Robotics at the University of Sydney. These will all build capabilities. We know we can produce payloads. We've done it before. We've put space shuttle science payloads up. We've been a part of the QB50 satellite consortium from the European Union. Biari is all Australian built. CubeRider is a Sydney company that put some hardware up on the side of the space station, up on the inside of the space station rather, so that high school students could upload code they'd written onto CubeRider's hardware. We can provide instruments for exploration in various missions. These are some of the instruments that have been put up onto Australian CubeSats. Additionally, Australians themselves have these capabilities and have generally taken their skills and talents overseas. I believe of the 2 instruments on the Curiosity rover that NASA JPL itself was a lead institute for, one of those instruments, the development lead was headed by an Australian, and similarly, I believe that same Australian is heading up the one of the instruments on the InSight on the Mars 2020 lander. So we've got a lot of Australian expertise, and we're also developing our capabilities in other mission segments as well. However, a lot of these companies are startups, and the ones that I've mentioned that aren't startups tended to be academic institutions. So the small companies with limited resources, especially in manufacturing talent and skills. So any assistance in this advanced manufacturing side of things, this is a niche you could consider getting into. Additionally, if you're part of an established manufacturing mob, this is another potential business line. Collaborations are always necessary. Space is dark and lonely. Make friends early, make friends often. These partnerships will always benefit people. So to conclude, Australia is a new player in space again. We were the 3rd nation to launch a satellite from our own territory back in '67, and then we kind of didn't do anything for about 40 years. CubeSats, smallsats, and the new space revolution, as it's called, which is driven by miniaturization in electronics, helping to broaden the cone of possibility. These all create opportunities for more people to do new things and continue broadening this cone of the possible. Australia is developing its own national capabilities for its own sovereign interests, and the plan is to do this development and tap into export markets to serve Australian interests. And thank you for your time. Like I say, I came out of the academy.
There we go. Thank you very much, Paddy Neumann. Now, you did hear a little bit, Dr. Neumann touched on there about some local businesses that are working in the space, because that's a thing that makes sense here. And our next speaker is Flavia Taranardini, who is the founder of Fleet Space Technologies. You would have seen her up on a slide earlier. Now, this is an Adelaide-based startup set to transform